We're going to send a sentence through the tokenizer and see what GPT sees. Import tick token, and then let's say nc for encode tick token.get encoding. Let's pass in cl100k underscore base text equals question we ask: how does GPT read my words? Alright, let me show you something strange. You create a string in Python. Name equals quote Michael quote. Nothing fancy. Then you try to change the first letter. Name bracket 0 bracket equals quote J quote. Python throws an error. You can't do it. Strings in Python are immutable. Once you create one, it never changes. And at first, this feels wrong, because almost everything else in Python can change. Lists change, dictionaries change, sets change. Your own objects change, but strings locked. Why? This is not an oversight. It is not laziness from the language designers. It is a deliberate design decision. Once you understand why, you'll start seeing the same pattern in every database, every programming language, and especially inside the large language models you use every day. Let's break it down. First, what is a string? In Python, anything between quotes is a string. Your name, a URL, an entire book. But text is misleading, because under the hood, a string is not text. It is numbers. Every character you see, every letter, every space, every emoji has a number behind it. Capital A, 65. Capital B, 66. Lowercase a, 97. Your computer doesn't store letters. It stores numbers that represent letters. And that mapping, the agreement about which number means which character, has a history. The first real standard was called ASCII, invented in 1960s, back when computers mostly spoke English. ASCII defined 128 characters, letters, digits, punctuation, a few control codes. That was it. And for decades, that was enough. Until it wasn't. Because ASCII couldn't represent the entire world. No Turkish sh or z, no Chinese, no Arabic, no Hindi, no Japanese. No accents for French, German, Spanish, no emoji obviously. If you weren't writing in plain English, ASCII couldn't represent your language. As computers spread around the world, engineers needed something bigger. Unicode fixed that. One system, every character, every living alphabet, ancient scripts, Egyptian hieroglyphs, cuneiform, mathematical symbols, musical notation, and yes, every emoji. And the brilliant part, Unicode is backwards compatible. Capital E is still 65. Every ASCII character kept its original number. Unicode just added more numbers on top. So the Turkish sh is 351. The Japanese character he is 26,085. And the fire emoji is 128,293. One universal standard, every character on Earth. All just numbers. Back inside Python, let us prove what we just talked about. I want to show you two things real fast. One, that strings work exactly like text. Two, that underneath they are just numbers. Let's start by creating a script by saying touch strings.py, and voila, here's the strings.py, and let's work inside it. I'll create a simple variable, call it name, and give it the value hex 1000 by saying name equals hex 1000. And now I'll print it to the screen by saying print name. Let's also ask how long it is using the len method by saying print len and name. Save it, run it by saying python strings.py. So hex 1008. 8 because hex space 1000. Each one of those is a character. The space counts, everything counts. Here is where it gets interesting. I want to ask Python directly what number does it use for the letter A. The function is called ord, and that stands for ordinal. Let's code these out first and say print ord. Let's pass in A. And let's go the other way too. Give Python a number and ask what character it means. That is the char function. Let's say print chr 65. So run it. 65 for A, and 65 comes back as A. Two functions, same mapping, two directions. And remember, this isn't just English. Let's try a Turkish character and an emoji. Let's code this out first. And let's say print ord and the Turkish character sh, which is she, and let's say print ord, pass in fire emoji. Save save it and run it again. So 351 for share, 128,293 for the fire emoji. Every character you can imagine is a number. Strings are just sequences of these numbers, wrapped up to look like text. So if a string is a sequence, we should be able to grab individual characters out of it. And that is exactly what we can do. Let me show you how, and then I'll show you the trick most tutorials get wrong. Say, clear this out first, and say text equals, like as before, x1000, and I'll grab 3 characters, the first one, the fifth one, and the very last one, by saying print text index 0 is the first one, print text index 4 is the fifth one, and let's say print text, watch how we do the last one, that is the tricky part, -1, save it, clear the terminal to see better, and then let's run it. H is position 0. Notice Python counts from 0, not 1. Most programming languages do this, takes a minute to get used to. Position 4 is the digit 1, because HEX space 1, that is the fifth character, but its index is 4 because we started counting at 0, and -1, that is the elegant part. Negative indexes count from the end. -1 is the last character, -2 is the second to last. You never need to calculate the length of a string just to get the last character. So now, what if I want more than one character? That is called slicing. Let's put this out first. Let's do slicing by saying print text. Let's pass in 0, colon, 3. You give Python 2 numbers separated by a colon, where to start and where to stop. Say print text, begin from the 4th index. Let's go till the end by leaving this empty. And let's say print text, start from the beginning by leaving it empty, and go until the 3rd one. Save it again. 0 to 3 gives us hex. That's positions 0, 1, and 2. The second number is exclusive. It stops before 3, not at 3. That is another one of the small details that trips beginners up. If you leave the second number blank, Python goes till the end. If you leave the first number blank, Python starts at the beginning. 3 ways to slice, 1 pattern. Here's the real power of this. Slicing works on any sequence in Python. Strings, lists, tuples, same syntax, same behavior. Learn it once, use it for the rest of your Python career. Here's the question the whole video is built around. We can read any character we want. Can we change one? Seems reasonable, right? It is our string, so let us just try saying text equals Michael text index 0, which is M, first letter. Try to change it to J, save it, clear the terminal, run it. String object does not support item assignment. Python is telling us flat out, you can read it, but you cannot change it. At first, this is infuriating. Why can I read position 0, but cannot write to position 0? What is the difference? The difference is memory. Here's what is actually happening. When I create the string Michael, Python goes to computer's memory and reserves a chunk, 7 slots, 1 for each letter, M, I, C, H, A, E, L. That block of memory is sitting right next to the other stuff, other variables, other strings, whatever the rest of your program has in memory. They are neighbors. If Python let me just overwrite one of those slots, there's a risk that I accidentally step on a neighbor, corrupt something I didn't mean to touch, create bugs that look like they came from nowhere. So Python draws a hard line. You don't modify strings, you replace them. Instead of changing one letter, I'll just point out the variable at a new string. Let's just quote this out first and say text equals Michael. Let's go ahead and print the text. Save it, clear it, run it again. So Michael, a ridiculous name, but it works. Notice what I did. I didn't edit the old string. I built a brand new string, Michael, with 7 different characters in 7 different memory slots. Then I took the variable called text and pointed away from the old string toward the new one. The old Michael string is still sitting in the memory, by the way, just orphaned, nothing points to it anymore. Eventually, Python's garbage collector sweeps it up and reclaims the space. This is immutability. Not you can't change strings, more like the strings don't change, your variable changes what it's pointing at. And this sounds like a technicality until you realize what it gives to you. It gives you safety. If I pass a string to some function, that function can never modify my original. It would have to return a new string. It gives you predictability. The string you created 5 minutes ago is exactly the same string right now. And most importantly, hashability. Remember dictionaries from the last video? Dictionary keys need to hash to the same number every time you look them up. If strings could mutate, every dictionary on earth would silently break. Immutability isn't a limitation, it is the foundation everything else is built on. So if we can't modify strings, how do we actually do anything useful with them? The answer is simple. Every string operation Python gives us returns a brand new string. The original stays untouched, always. Let me show you ones you'll use every single day. First, adding strings together. You just use plus and you can multiply a string by number to repeat it. Let's create a greeting message by saying greeting equals hello plus empty space plus print out greeting message, and let us say separator equals equal sign times 20, and let's print out the separator. Save it, run it. Hello world, built from 3 separate strings glued together. Python made a brand new string out of those 3 pieces and 20 equal signs that is useful when you want a quick visual divider in your terminal output. 1 line of code, 20 characters in result. Here's the part I want you to really notice. I'll create a sentence, transform it to a bunch of different ways, and then print the original at the end to prove it never changed. First of all, let's say text equals, say Python is amazing, and then let's say print text, use upper method to make all caps. Let's say print lower to make all lowercase. Let's replace a word in our string by saying print text.replace. Let's get rid of word amazing, replace it with powerful. Let's print out each word as separate by saying print split, use empty space. Finally, let's print the text, save it, run it. Look at this. Upper gave us Python is amazing, lower gave us all lowercase, replace gave us Python is powerful, split broke it into a list, 3 words. Python is an amazing. 4 transformations, and then I printed the original again. Python is amazing, exactly as I created it. None of those methods touched the original. They all returned new strings. If I wanted to keep the uppercase version, let's say, I would have to save it into a new variable. One more really useful one. Clear it. This is something you'll use the moment you start handling real data. User input is messy. It comes with trailing spaces, line breaks. Strip cleans that up. Let's say messy equals white space, hello, world, again, white space. It's a messy message like we said, and let's say print. Let's fix it by saying messy dot strip, save it, run it again. Look at the original. Spaces everywhere. Strip removes all the white space from the start and the end. Returns a clean new string. The second you're taking data from a form, an API, or a file, strip becomes your best friend. Pay attention to what I just showed you with split. We turned a sentence into a list of words. Hold on to that thought, because that is the very first step of how AI reads your message. Before we get to the tokenizer, the AI part, there is one tool I want to make sure you know, because you will use this every single day. It is called f-strings, short for formatted string literals, but nobody calls them that. Everyone calls them f-strings. I'll set up 2 variables, a user and a video count, by saying user equals x videos equal to 3. Then I'll build a sentence that uses both of them. Watch the little f before the opening code. That is what makes this work. So let's say print f-string, let's say in curly braces, user has uploaded, curly braces again, the videos. So let's save it and run it. Hex has uploaded 3 videos. The f at start turned on a special mode. Anything I put inside curly braces, Python evaluates it as code and then drops the result right into the string. Code means really code, not just variables. Anything you can run. For example, let me do some math right inside the braces by saying print f-string. So let's say next here, say videos plus 50 videos. Save it and run it again. So as we can see, 53. Python did the addition inside the string. You can call functions in there, you can format numbers, and you can do conditionals. Anything. Before f-strings existed, they only came in Python 3.6, which is fairly recent. We had to use the format method or %signs from the old C days. It was ugly and awkward. The f-strings are how you will build almost every string in modern Python. Get comfortable with them and use them instead of concatenation wherever you can. Alright, everything we've done in this video was leading here. How does GPT read your words? So let's clear all of it. You've got every piece of the puzzle now. Besides strings are sequences, characters are numbers via Unicode, strings are immutable, which means they're reliable, hashable, safe to pass around. So when you send a message to GPT, first thing that happens is the model takes your string, turns it into a list of numbers. But here's the trick. It doesn't use 1 number per character. That would be way too many numbers, too slow. Instead, it groups common character sequences together. Each group is called a token, and each token has its own ID number. Common words get their own token, rare words get broken into pieces. Let me show you exactly how this works. You can run this yourself. First, I need to install a library. It is called TickToken, made by OpenAI. This is the actual tokenizer that GPT-4 uses, not a simulation, the real thing. Let's go ahead and install it by saying pip install TickToken. It's done now. We're going to send a sentence through the tokenizer and see what GPT sees. Import TickToken, and then let's say enc for encode TickToken.get encoding. Let's pass in CL 100K underscore base. Text equals question we ask. How does GPT read my words? Tokens equal ENC encode. Pass in text variable we created, and then finally let's print out the tokens. Alright, save it, clear the terminal, run it. So this right here is what GPT sees when you send that sentence. A list of 8 numbers. Every conversation you ever had with ChatGPT, every message, every reply from the model's perspective is a list of numbers, just like this. So let's decode these one by one and see which word turned into which number. I'll loop through the tokens and for each one decode it back into text by saying for token in tokens print token, comma, the arrow to show us ENC decode token. It's a for loop, as you can see, and let's run it. So look at this carefully. There are a few things worth noticing. Some tokens are entire words on their own. Some include the space before the word. You'll see the leading space in the output. The question mark at the end got its own token too. And finally, the GPT didn't split this on white space the way a human would. It learned from billions of sentences which character combinations appear together most often. Common words, one token. Rare words broken into pieces. Let me prove that with 2 quick examples. Take a really long rare word by saying print ENC encode, pass in that long word and type this establishmentarianism. I don't know if I wrote that correctly, but let's go and enter common word, which is the most common word, save it, clear terminal, run it. So as you can see, first word, that is one English word, 28 letters, but broken into multiple tokens, because the full sequence almost never appears in a training data, but its pieces, anti, this, establish, are common on their own, and the most common word in language is a single token, one number, and done. This is what people mean by a model's context window. When you hear 128k context, that is 128,000 tokens, not characters, not words, these tokens. And every single token is just an integer in memory, which becomes bits, which becomes electrical signals, flipping transistors inside a GPU. Now you can see the full chain from your thought to the hardware. Begins, thought, like we said, goes into a keyboard, goes into a string, goes into characters and numbers, tokens, bits, and transistors. Strings are the bridge. So, why are strings immutable? Because the memory is finite. Because safety matters. Because predictability is a feature, not a bug. Because the systems built on top of strings, dictionaries, hash tables, databases, large language models, all depend on one thing, a string. Once created, stays exactly what it is. You don't edit a string, you replace it. That is not a limitation, that is the entire philosophy. Knowing the syntax is useful, but understanding the decision behind it is what makes you a problem solver. Next up is lists, the structure behind your recommendation feed, your browser history, and every queue in every modern application. Unlike strings, lists can be changed, which opens up a whole new world of design decisions. Sorry for today, because I was feeling under the weather. Had the flu, temperature, and all of it. But thanks for bearing in and listening to me till the end. I am Hex1000, logic behind the code, signing out.